Sample problem S09-03. Cars moving along horizontal roads are about to be stopped when they hit a protective barrier. All of the cars are the same size and shape, but they are moving at different speeds and they have different masses. The barriers are all identical and exert the same constant force. And as always in a physics problem, this kind of thing, the same constant force, is clearly going to play some sort of role. So we are asked to rank the time that it takes to stop the cars as the barriers apply the same constant force. They're definitely hitting us over the head with that. So since I don't want to look at this. So what we want to say is the delta, the impulse, is going to be related to the force times delta t. And we know the force is the same. So that means that it's going to be delta t is going to be ranked the same way as I. If I figure out which ones have the biggest I, then I have figured out which ones have the biggest delta t. And then we want to also say, but I, in addition to being f delta t, I is also delta p. So if we figure out which one has the greatest magnitude, delta p, then we can figure out that would be the same as the biggest I, which is the same as the biggest t. The goal here always is to link the thing we're looking for to something that we can get that's in the same ordering. Now, delta p is delta of mv. And the key thing here in some sense is that they all end at 0. And then it's minus the mass they had at the start times the velocity they have at the start. The mass doesn't change during the problem, the velocity clearly does, but delta p is going to be minus mv initial. So now we need to go up here and say to have the largest delta p means to have the largest m times v, and if we can figure out the largest delta p, we have the largest I. If we figure out the largest I, we have the largest delta t. So in the end, all we need to do is figure out whoever has the largest initial momentum will also have the longest time to stop. And I guess all of that boiled down to a pretty simple statement. The larger initial momentum with a constant force means it takes longer. So that's what goes on here. If we look at this, we would have, we'll look at, for instance, box A. We have 3,000 kilograms times 10 meters per second, or 30,000 units of momentum. But in box B, we have 1,000 kilograms times 20, so that's 20,000 units of momentum. And here we have 1,000 times 30, and that is also 30,000. And then finally, we have 2,000 times 20, or 40,000. And so the ordering for momentum is D is more than either A or C, which is more than B. But remember, the ordering for momentum is the ordering for the magnitude of the change in momentum, which is the ordering for the impulse, which is the ordering for the time. So in the end, we've ended up with the same, right? This is our answer for the times as well as for the momentums.